All right. Sorry here. Get a little organized. Try to get organized. All right. So, what's that? I am. Thank you. Thank you, Allie. I appreciate that. Somebody, I need somebody.
Because I wasn't sure if I need to write it down in detail or not.
I wanted to make sure. All right. So, this is actually number 4. And so it was the integral still from -5 to 5. It was the whole thing, right? And it was the trapezoid rule. So, one of the things we're going to write down here in a few minutes is, the left, the right, the trapezoid, the midpoint rules, just in generic form. And what we want to eventually be able to do is to be able to write them out without having to have the picture, right? But yet, in our head, as we're writing them out with the f, when we write f of -5, we understand that's the y value at -5, and that is the height of a rectangle, or it is one side of a trapezoid, right? Do we understand that? So when we do a trapezoid, okay, basically, rectangles usually have a height and a width, and we've already determined here the width is 2, right? The width is 2 on this one because you're doing 5 subintervals. We're doing a T5 here. Okay, is that right on number 4? And so the way you draw a trapezoid is you go up to the curve on the left edge, and then you go up to the curve on the right edge, and you connect. And that makes a trapezoid. Unless one edge is going up and the other edge is going down, or one of the edges doesn't go anywhere. It's right on the axis. Then it actually isn't a trapezoid. We talked about that right at the end, right? It might be a triangle or some weird thing. Well, that's what happens here. So since our width is 2, which is right here, right, we're going to go to the left edge, down to the curve. And we're going to go to the right edge, and in this case, up to the curve, and then we connect. That is a trapezoid. It's not really a trapezoid, but for calculus area under curve purposes, that is a trapezoid. It's really 2 triangles. Okay? So, left edge of the interval, up to the curve, right edge of the interval, up to the curve, connect. That's a trapezoid. So, it would be these 2 triangles, really. But think about how we would write this. We would go 1/2, and then what would be the left base of the trapezoid? F of -5 plus, this is like the B1 plus B2, F of -3 times that, which is 2. Again, we would not have to have this picture here to know this, right? To know this, we would not have to have this picture. If we know -5 to 5, and we know the width is 2, we know our first trapezoid would start at the left edge, -5, and then since a width of 2, we'd go over to -3, would be the other side of our subinterval. And so we can write all of this down without any of this picture over here. Without even knowing that, hey, one of those goes down, one goes up, and it's weird. We wouldn't even have to know that. We wouldn't care, right? Our trapezoid is going to look like this. And the next one's going to be 1/2. We can write the next one without even looking at the picture. It's going to be what? 1/2. Because the right edge of this one is going to be the left edge of the next one. So this is going to be f of -3 plus f of -1. You see what I mean? And then times 2. So we want to be, well, I said we want to eventually. I think now we should, right? Right now we should be able to do this. We should be able to look at a trapezoid, say, hey, we're going to do 5 trapezoids. We look at this problem, forget the picture right now. We look at this problem and say our integral is a width of 10. We're going to do 5 trapezoids, so they're 2y. I'm going to start at the left edge as -5. The right edge of it will be -3 because of the width of 2. And then I just keep moving over until I have the rest of them down. Now, let's go ahead and put in the numbers on this one. You're right, f of -5 is -2. F of -3 is how much? 2. That's -2 plus 2. 0. So this is area of 0. Well, isn't that what you saw right here with those 2 triangles? One's negative, one's positive. They're the same. That is going to be a 0 area. So the formula makes it work. right? I mean, it works, okay, even though it isn't a trapezoid, but for our purposes, it really is. Okay, and then we just keep going, so it'd be 1/2, and then it would just keep, negative f of negative 1 plus f of 1 times 2, and then the last one, or it's not the last one, I guess we got 2 more, 1/2 f of 1 plus f of 3 times 2, and then finally 1/2 f of 3 plus f of 5 times 2. And there's your 5 trapezoids, right, all written out. So again, patterns. You see the patterns. You see the important information. The total width comes from your integral. How many trapezoids or rectangles you're doing tells you how wide the thing will be. And once you have that information, you're off and running, okay? Now, if it was a left rectangle we were doing, we start at the left edge, but we don't use the last one, right? We don't use the far right edge. But if it's a right rectangle, what happens? You don't use the first one, right? You don't use f of negative 5 because your right rectangle would go here and back. So it would go to f of negative 3. And it would go all the way to the right edge. And then, of course, the midpoint's kind of that weird one where you're in the middle. Okay, so you have to, and that's why, to be honest, we kind of avoid midpoint if we can. Because that's just a little harder. All right. Good question. That's good discussion. What else? Anything else on that?
What was the answer for that one?
I don't know. Somebody got the answer that they're
I'm not sure if it's right, but I got 6.
6? Well, if that many people got 6. Here. This. We did. Everybody did. Well, okay. Here, we can read them real quick. Number 1, I have 4. Number 2, I have 8. Number 3, I got 7.
I got 7.
Oh, it's like
Now, the midpoint one, don't you have to estimate a little bit? Or not really? Well, okay, let's go through them. So on 3, the first one would be at negative 4, right? It would be f, or actually this is g, isn't it? I used f, it's supposed to be g. You used f too. So it's f of negative 4, which would be 0. And then it's f of negative 2, which is 3. And then it's f of 0, which is 2, so that's 5. Oh, I forgot to multiply by my 2, didn't I? So it'd be 3 times 2 is 6, and 2 times 2 is 4, so far we have 10. G of 2 is negative 1 times 2, that'd be negative 2, that'd be 8. And then G of 4, oh, that's it. G of 4 is negative 1/2 times 2, so that'd be negative 1. So you must have, if you got 9, you must have added 1, not done negative. So it should be 8, take away 1 is 7. Okay, 4 is 6, okay, what you guys just said. 5 is 7, or 9. Wait, what did I just say? Like I said, 5 is 3. Number 6 is 7?
Yes.
Okay. Sorry, skipped over that one. Number 7 is 24. What did we go to then? 10? 26. And then 16. 16, is that right?
Yeah.
16. L4 is R4, M4, T4, and the exact value, did you remember to do that? 9 1/3. What was the function on that one? I can't. What was it? So that'd be 1/3 x cubed from negative 1 to 3. So 3 cubed is 27 times a third is 9 minus, and then you put a negative 1 in there, you get negative 1/3. So 9 plus a third, 9 1/3. Yes. midpoint. Okay?
That's just kind of like how you plug it in. I got notes on that.
All right, let's do that one without the picture. You're talking about the calculation. So it was negative 1 to 3 of x squared dx. So let's just practice this right now. You're supposed to do an M4. So let's don't even draw a picture, okay? So what would you be thinking? You'd be thinking first, what's the width? 1, because the total width is 4. 3 minus negative 1 divided by 4, so that's going to be 1. So that means my first rectangle, and again, it doesn't hurt to, sometimes what I will do on these, even if we don't have to draw a picture, is I'll just draw myself like an x-axis. I'll just, I'll go off to the side here, I'll draw myself an x-axis, okay, I'm going from negative 1 to 3. I'm going to divide that up into 4 subintervals, okay? So I'm going to have 1, 2, 3, 4, so that's going to be 0, 1, 2. So I just can look at it, it just gives me numbers to look at, almost like number line. So my first midpoint is going to be where? Negative 1.5. So I'm going to put negative, or not 1.5, but 0.5. Okay, times 1 plus f of 0.5 times 1 plus f of 1.5 times 1 plus f of 2.5 times 1. Now again, I want you to put the times 1 there for right now. I want you to see height and width, height and width, height and width, height and width. When you look at this, I want you to see rectangles. 1 rectangle, 2 rectangles, 3 rectangles, 4 rectangles. Okay? And adding them up. Okay? So now what are you doing? You're putting this in here and squaring it. So negative 1/2 squared would be 1/4. And 1/4. 2 1/4. Right? 1.5 would be 2.25. And then 2.5 squared would be 6 1/4. 25 squared is 625, isn't it? 6.25. So what is that? 8 1/2 and 1/2 is 9. Okay? All right. But again, see how we can draw? We want to be to the point, or beginning to the point where we can just write these rectangles out. Right? Maybe you do this much. Now, you were supposed to actually draw the picture. But the rule is going to be single digit. You have to write them out by hand. You don't have to sketch the actual rectangles unless it says. So on the quiz, the next quiz we take, and somebody was asking the term, I think the term is a week from Tuesday. So we'll have one more quiz and probably a homework grade that'll go in there. We have a quiz next Thursday. That's then your gateway, right? You get your gateway passed, you can get that grade in there yet too. Okay, some of you already have that grade in there. So that would be the grades we'll still be having this term. Now, so on that quiz next Thursday, there will be some that will say draw a sketch, but there will be others where it just says, evaluate M4. This is what I want to see, right? I want to see you're going to get points for having this written out, and then this part you can do. Trying to think if it'll be calculator or no calculator. I don't know. It doesn't really matter because, like I said, if it's going to be calculator, I still want you to write this out because by then I will have given you this calculator program that you can just type in and get the answer for M4. So that's why I'm saying if it's single-digit subdivisions, you have to write it out, okay? Because I want us to get used to that pattern. But if I ask for an M10, you could just give the answer. Yes?
If it's a question when we don't have to draw the sketch, can we still draw it?
Sure. Absolutely, yeah. Absolutely, you can still draw it, yep. And like I said, I usually draw part of it at least. I'll draw the x-axis, I'll draw those so I can see my subdivisions. I will do that anyway in a lot of these problems. Okay, let's move along here. I want to try to give you some work time on things here. Okay, here we go. Okay, so yesterday we had this, right? We wrote this down, the Riemann sum. And when you hear Riemann, you think what? Rectangles. R for Riemann, R for rectangles, right? Well, you might think some other things too, but rectangles. Riemann sum. Adding up rectangle areas. That's what it is. So trapezoid approximation is technically not a Riemann sum. Okay? left, right, midpoint, or it could be some point in between. Now in your book, there is a decent picture in your book. Matter of fact, I might be able to pull that up here. Let me, here we go. This would be a Riemann sum. We were talking yesterday about how we talked about the C sub I, pick some sampling point, pick delta xi is the width of the ith subinterval. Here, this is a Riemann sum. It's 6 subdivisions. They're just not equal subdivisions, okay? This one, you know, is obviously thinner than this one and so forth. And look at the sampling points. This one looks like it's somewhere in the middle, but a little left of the middle. This one's a little left of the middle. This one looks like it's on the right edge. That one's on the right edge. That one's a little right of the middle. That one's a little right of the middle, right? I mean, but they're all, each one of those is a rectangle approximation. Another term you sometimes hear is inscribed rectangles and circumscribed rectangles. What's an inscribed rectangle, do you suppose? Under the curve. So if you had a curve like this and you were supposed to find inscribed rectangles, then you would have to look at the subinterval and find the lowest point there, and then that would be your sampling point to keep your rectangle entirely under the curve. And circumscribed rectangles would be ones that are completely over the curve. So those could be at various places as well. So sometimes you'll see that. I won't ask about it probably on any of our quizzes, but in the AP test in our packet stuff, sometimes you may see that. Something about inscribed and so forth. Okay? So that's still a Riemann sum. It's just that we won't do it very often. Now, where that does come up, where you do get into those kind of situations, is if you're given a table instead of a graph or an equation. If you're given a table of data and your x's are irregular, you got 0, then 2, then 5, then 9, they're unequal widths. And if you were going to do rectangles there, okay, then you would have to go with those widths, okay? So when you write it out, like we were doing back here, let's see, where was that at? When we were writing this out, you may not have equal width things. You would just take the points in the table that you were given, okay? We'll get into that a little bit more. Maybe we probably do some of that tomorrow, actually. Right now, we'll stick with graphs and equations. Okay? All right. So here's what I'd like you to maybe write down in your notes. It's up to you, but this is kind of how we'll talk about this here a little bit. And that is just the generic formula for a left, a right, a midpoint, a trapezoid. Okay? So it's up to you, but this would be how we would think of this. So we would say, okay, if I'm going to write a left, so this is, we don't need the picture kind of thing, like we were just talking about. So if I was going to write down a left rectangle, what would I start? Well, I'd start with my height, my f of, and I'd always start at the left edge. And we said we were going to call that x sub 0 yesterday, right? So it's going to be f of x sub 0 times my width, then f of x sub 1 times my width, plus dot, dot, dot. And I would always stop one short of the right edge. If the right edge is x sub n, then I'm going to stop at x sub n minus 1. Okay? And that would give me n rectangles, because I started at 0, went to n minus 1. All right? And so right rectangles would look like that. The right rectangle, we don't include the left edge, right? We go to the next point over, which would be x1. So it would start with f of x1 times delta x, then f of x2 times delta x, dot, dot, dot. And we would end at the right edge, which we said was x sub n. Now, just notation-wise, this one is kind of the nicest, because it starts at 1, ends at n. So if we have a choice, as you're going to see here in a minute, if we have a choice of one of these to pick, we're going to use right rectangles, because just notationally, it's just a little nicer. Don't have to start at 0, start at end at n minus 1, that kind of thing. Midpoints are really a mess because then what we have to do is we have to find the midpoints. Now, I called it M1, but typically what you'll see here, let me write it in red here. Typically what you'll see for this is x1 or x0 plus x1 divided by 2. And it just is really a mess because that's what the midpoint is. It's your left edge plus your right edge and then divided by 2. That's what your midpoint is. So I didn't even want to get into writing that, so I just called it M1, M2. You'll just have to find them, right? You'll just have to find what the midpoints are. So notationally, that's a challenge, and so we'll stay away from midpoints when we're doing this. And then, of course, trapezoids aren't even Riemann sums, and they're kind of messy as well. But the thing that what you'll get from writing this is, okay, here's my trapezoid formula. We start with the left edge, which is x0, just like the one that Allie asked about when we did number 4. So we kind of went over this already. So we start with the left edge, which is x sub 0, plus the next one over, which is x1, and then times our delta x. And then our next trapezoid will start at x1 and then go over to x2. And then the next one will have x2 and x3. On, and then our last one will be xn minus 1 and xn. So we start with x sub 0 at the very beginning, and we end up clear at the right edge also. Okay, so that's just kind of putting those into generic form. Now, here's what we're going to try to do with this. The whole idea I told you yesterday was about seeing patterns. We're going to try to get to a point today where we can see and show what it is that your calculator is doing. How is your calculator? How is there a formula, inside your calculator program to come up with these? Okay. And we're going to need a lot of mathematic notation to be able to do this, and we will use our calculators here a little bit later too. Right now we want to review this notation. This is a Greek letter. Anybody know what it is? Sigma. Did you do this a little bit last year? Tiny bit?
I remember what it's called.
Seems like we do a little of it. Not as much as we used to, so we're going to spend a little more time reviewing it here. Sigma notation is used for what? Sums, right. It's a Greek letter S, stands for sum, so sigma is used to represent sums. Well, that sure fits with what we're doing right now, right? And that's what we're doing. We're doing sums, Riemann sums. We're adding up these integrals. And writing sigmas had to do with notation for writing sigmas and formulas and shortcuts for writing sums. And that's what we want to do here as well. When you look at how we're writing out all these, imagine if we wanted to write out an L100. It'd be awful, right? It's bad enough writing out 5 of them or 8 of them or whatever, right? If we would write out 100 of them, it'd be a disaster. So we want to come up with some shortcuts for this, and that's what sigma notation does for us. So all right, so we're going to do a little bit of this just together here. All right, switch gears for a second, learn a completely different problem. It'll be apparent in a few seconds why we're learning this seeming unrelated to integration. That's what I just talked about. So let's say we were going to find the first 4 terms of this sequence. 1 plus 2 plus 4 plus ... equals blank. How did you arrive at this answer? Like it says, the problem is the rule for each term is not apparent. We introduce blah, blah, blah. What would you assume in this problem right here? How would you add up the first 5?
Split by 2.
Well, you better get the next 2, right? I mean, you only got the first 3. It looks like you're multiplying by 2 each time, so it looks like the next one is 8 and 16, right? So it looks like you multiply by 2, and then you would just add them up. There's only 5 of them, so you can just add them up, right? No problem. Now, it says we're going to introduce this notation called sigma notation. The sum of n terms, a1 plus a2 plus a3 plus dot 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 an, is written like this, where I is the index of summation, so that's this down here. So we got the sigma down here, we got I equals 1, up here we got n. This is the beginning point, this is the ending point. It always goes by ones, we can't go by twos or by threes or negatives or anything else. It starts here and it always goes up by 1 until there. Okay? Sigma notation does not help you find the sum. It only gives you a way to write the sum. Okay, so we're gonna help with that as well. Okay, so let's do these right here. So sigma of 3. Now this, how do we read this? I would read this as sigma of 3 or sigma 3. I equals 1 to 8. That's how I would read this. So what is this really saying? Remember, sigma means sum. Sigma means add. Well, here'd be an easier one. This would be an easier one. Let's actually do 2 first. Sigma I, with I going from 1 to 6. And we want to take a crack at what they're asking you to do there.
All the terms added to 1 6 equal I.
So what would be the terms?
1,
1 plus 2 plus 3 plus 4 plus 5 plus 6. In other words, this in here is a formula to find the terms when I goes from a 1 to a 6. So I starts out a 1, you plug it into there, and you get a 1. That's the first term. When I is a 2, we plug it into there, and that's the second term. I is a 3, I is a 4, I is a 5, and I is a 6. It gives you the terms. And then since it's a sigma, that means you add them. So you would just add it. So 3, 6, 10, 15, 21. So the answer to this one would be 21. This one here, number 3, would be what? 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. Right? Start with a 1, plug it in, 1 squared is 1, then a 2, then a 3, then a 4, all the way to 7, and then add those up. We'd get our calculator out and we would add them up. Okay? 5, 14, 30, 55, 85, 91, 140. Okay? What about this one? Oh, that's a negative 2, isn't it? So negative 2 cubed is negative 8. Negative 1 cubed, negative 1. 0 cubed. Notice it doesn't have to start at 1, does it? Doesn't have to start at 1. But it's got to go up by 1. 1 cubed, 2 cubed, and 3 cubed. 27. What's that add up to? 27. Okay? Jot those down, actually, because we're going to check them here in a minute with some. So 21. Okay, now back to the first one. What's the first one? 3 plus 3 plus 3 plus 3 plus 3. There'll be 8 of them. Right? Because what that's saying, when I is a 1, you plug in a 1, there's nowhere to plug it. So when I is a 1, this is a 3. When I is a 2, this is a 3. When I is a 3, this is a 3. When I is a 4, this is a 3. 3 plus 3 plus, so this is just 3 plus 3 plus 3, 8 times, which of course would be 24. So that's basic sigma notation. Okay, just expand it out and add it. Now, the problem would be, much like our rectangles, what if this said 1 to 100? That would be not fun. Writing down all those numbers from 1 to 100. We're going to do that here in a second. Well, we're not going to write them all out, but we're going to find that sum. We're going to talk about how we do it. So, like it says here, sigma notation doesn't help us calculate the sum. It just helps us to write out the sum. Okay, it's a shortcut way of writing out these sums. Well, think about it. What you guys did today's homework was write out these sums, these long, well, not that long, 4 to 5, whatever. We're going to come up with a shorthand way of writing it using the sigma notation, right, instead of writing them all out. But we want to go both ways. If we have a sigma, we want to be able to write it out and then be able to find the sum without having to add them all up, especially if we have like 50 of them or 100 of them or something like that. Okay, so they've got some properties down here. So the next thing, so you guys got those. So, okay, so the next thing right here, we have some basic properties. Like if I have a sigma and I got a formula and I've got a constant multiplied there, I can pull the constant out in front. That looks familiar. When I got a constant inside the sigma, I can pull the constant out in front. If I've got two things, two parts, like if I had an I squared plus a 3i inside here, I can, with plus or minus, I can separate that out into separate sigmas. That looks familiar. Okay? Right? So those are some properties of sigmas that I can do. So, let's, hang on here a second. I kind of forgot where this is going. Okay. What's that?
Are you supposed to write them down?
No. All the formulas? You can. Yeah. You can. I don't know if it's that important, to be honest with you. They're easy. I mean, they're just the same thing we've done with integrals, right? You can pull the constant out in front, or you can split it apart. But yeah, if it'll help you, go ahead and do that. And I want to do a couple of these here anyway. So, let's see here. Yeah, let's do these two right here. Let's do 6 and 7 right here. All right. So let's look at 6 here. So just simple one. This will be kind of the beginning of your homework today. I'll have some of this. So you got I equals 1 to 5, 5i minus 2. So what will I write down first? I just want to add these up. So I start right here. I equals 1. What do you get? 3 plus 8 plus 13 plus 18 plus 23, right? Plug a 1 in for I, plug a 2 in for I, plug a 3 in for I, plug a 4 in for I, plug a 5 in for I, right? Find the sum. And then we add that up. That's 11, 24, 34, 42, 62, 65. That'd be 65. Okay, now, let's just talk about going in reverse here. You're not going to have to do this too much, but a little bit. But most of the time, we'll have it kind of easy for you. This is something I know you did in Mrs. Payne's class, for sure. I think the other advanced math classes do it too. But what about if we wanted to go in reverse? What if we wanted to write the sigma for this? And typically, we start with 1. Typically, unless there's some really good reason not to start our sigma at 1, we would start at 1. Usually we use I, J, and K. Those are usually the letters we use in a sigma notation, just traditionally. So 1, 2, 3, 4, 5 terms. So that would tell me I'm going to go 1 to 5. So let's say we had this, and we were supposed to come up with this formula. I think you called it an nth term formula last year. Finding an nth term formula, okay, is what you're doing. Well, here's how I would do this. I would notice that these are going up by how much? 5. Repeatedly adding 5 should make you think of multiplication, because that's what repeated addition is, right? 3 plus 3 plus 3 plus 3 plus 3, 8 times is 24. You repeatedly add 3, you're multiplying. What's repeated multiplication? What's x times x times x times x? It's a power. Exponents is repeated multiplication. So if I see a problem that's repeatedly multiplying by something, I'm going to think power. if I see something that's repeatedly adding the same thing, I'm going to think multiply. So in this problem, when I saw that it was repeatedly adding 5, I'm going to think 5i. Then I'm going to test it. Well, when I is a 1, I'd get 5. Is that my first term? No. It's 2 less. When I is a 2, I get 10. Is that my next term? No. 2 less. So then I'd say, you know, not too bright, but at some point I'd say, oh, I just need to subtract 2, and then I'd have what I want. So 5 times 5, you see what I mean? So it's not too hard to come up with these. You know, if you had this. Now, I'll tell you how it'd be a lot easier. Instead of me giving you this sum this way, what if I'd have given you this? 5 times 1 minus 2 plus 5 times 2 minus 2 plus 5 times 3 minus 2 plus, you think you could have seen the pattern then? Do you suppose you'd have seen the pattern? Where would the I have went? Where the 1 and the 2 and the 3 goes, right? The stuff that stays the same each time is just going to be in the formula. But the thing that changes, the thing that goes from a 1 to a 2 to a 3 to a 4, that's the I. That's what the I does, right? That's part of what you guys are going to be doing in today's homework as well. I'm going to give you some things that look like this. Not like this so much. I'm going to actually give them to you in this easier form, right? And you just got to see the pattern. Remember I said this is about seeing patterns. Okay, it's connecting back to what we're doing with integrals, so you'll see here in a minute. All right, next thing. All right, so let's say we had this one right here. Now there's a story behind this problem right here. I equals 1 to 100. Okay, oops. So let's say we had, so write this down. Let's say we had sigma I equals 1 to 100, and the formula is I. Okay, so what's that asking? What do they ask me to add up? 1 plus 2 plus 3 plus all the numbers to 100. Now, the story goes that a famous mathematician, I think it was Gauss, I think was this particular mathematician. When he was young, he was so smart, genius, like many of you probably. You were in elementary school, and you were so far above what was being taught in kindergarten, first grade, that you might misbehave because you were born, right? I can see that happening to some people. Still doing it now. Anyway, so the teacher was tired of it, sent him to the corner, and said, don't come back until you've added up all the numbers from 1 to 100. So he goes to the corner, and in like 5 seconds, he comes back, and he had the answer. Now, I don't think this really happened, but that's the story. How did he do it? Well, he looked at the numbers from 1 to 100. Now, again, he was a genius, right? He paired them up. You ever seen this before? Right? Each pair adds up to what? 101. Times how many pairs? 50. Now, if you're a kindergartner, you can multiply 101 times 50. That's pretty good. Right? 5,050. Right? And that's what they would add up to. Now, how did he do that? Well, he took the first term plus the last term. Right? Well, no, I'm sorry. It is first term, last term. But in this case, it's a number of terms. Right? Plus 1. And he multiplied that times, how many pairs were there? Be that number of terms divided by 2. Right? And that is actually the formula for any sigma I for any number of terms. So in other words, now let's go back to what I said about sigmas. Remember what we said about sigmas? A sigma notation doesn't help you find the sum. It just gives you a way to write the sum, and you can expand it out. But for finding the actual sum, we might need some other things, some other tools, some formulas. And here is a list of some. And I'm not going to make you memorize these. I'm going to give them to you on the quiz, but these are them right now. You might want to write them down now so you've got them for your homework. These are called our summation. We're going to call these our summation formulas. Right? These are summation formulas. Okay? So the first one says if you have sigma of a constant, this is an easy one. Remember we had a 3 there and we went from 1 to 8. It was just 3 times 8. 24, because you have 3 plus 3 plus 3. So if you got sigma of a constant, it's just C plus C plus C plus C n times. That's going to be C times n. So that's easy. Okay? Here's the one we just did. Right? If you have a sigma I from 1 to some number n, it's simply going to be n times n plus 1, all divided by 2. Yes?
I didn't start one.
Then these formulas would not work. Right. So we want I to start at 1. And the ones where we're going to do it, they're going to. Okay? What about sigma of I squared? 1 plus 4 plus 9 plus 16, so forth. Right? Well, the sum of a bunch of squares added together actually has this formula. And we're not going to worry about where that one comes from, but it's similar to how we got this other one. But n times n plus 1 times 2n plus 1, all divided by 6. Those we will use for sure. I don't know if we'll get into this one, but you'll be given it if we need it. And if you have a sigma of I cubed from 1 to n, then it's n squared times n plus 1 quantity squared, all divided by 4. So let's test that on one of those we had written down earlier. What was the one we had? We had I squared from 1 to 7. Wasn't that one of them you guys had? Isn't that what we did? Wasn't the answer 140? It was sigma I squared 1 to 7. The answer was 140. We wrote it all out. Okay? Well, let's use our formula now for this one. So instead of having to write it all out, our n is our 7. So we would have 7 times 8 times 15 over 6. Now, if we had our calculator, we could just go ahead and type that right in. If we didn't have a calculator, you could cancel a 3 there with that. You could cancel a 2 there with that 8. 7, 4 times 5 is 20. 20 times 7, sure enough, 140. If we had our calculators, we could do it quite easily as well. Now, turns out that your calculators will actually just do this sigma, which we're going to use that factor in a minute anyway. But you can just type this sigma, right? Same place in your calculator where you get the integral symbol and the derivative symbol. There's a sigma symbol in there. And you can just type this sigma right in there. You don't have to use I. You can use X or whatever letter you want. And it'll do it for you, which is nice. Okay? So so sigma just allows us a way to write a sum. These formulas allow us a way to just calculate sum. Now, we can put this together. So you really see on the homework, it's the same thing. We're going through a sequence of steps, and we're building each thing from what we did before. Okay? So now I can take those formulas, those other formulas we used earlier, and I could do this. Let's do this one down here. This is more fun. Let's do this one right here. Let's do number 16. Okay? So one of the things we said we could do with a sigma, if you got 3 things added together, is do what? Split it. So here's a sigma I squared minus a sigma 4i plus a sigma 2. And the I goes from 1 to 60 on all of them. What's the other thing? Look at that middle one. What's the other thing we said we could do? We said we could take out the 4 and pull it outside. Okay, look what we've just done. We've now written these in such a way I can use those formulas we just wrote down. I've got a sigma I squared, I got a sigma I, and I got a sigma constant. Right? So there'll be a few, maybe an homework where you're doing this. Okay? So now, what was sigma I squared? It was n, which would be 60, times n plus 1, which is 61, times 2n plus 1, which would be 121, all over 6, minus 4 times sigma I. What was sigma I? That was n, to be 60, times n plus 1, 61 divided by, I don't know, you guys wrote them down. What was it divided by 2? It was divided by 2, right? It was n times n plus 1 divided by 2. Plus, what's sigma 2 from 1 to 60? 2 times 60, right? It's just 2 added up 60 times. And now we can get our calculators out and just type that in. Now, I understand what you're thinking. Well, why didn't we just type that into our calculator to begin with? Well, you could to check it, right? But on your on the next quiz that we do, again, if it's a no calculator, I would make the number smaller, so you could do that easier. If it's a calculator one, I'll want to make sure and say show your work. You know, if it says use the summation formulas to do this sigma, I know your calculators can just do it, but I want to see your work like this. I want to see you split it apart, do this. Okay, so I'm not sure which way we'll go with that on the quiz, but make sure you're using the formulas. Okay, so you multiply that all out and whatever. I don't really care right now what the answer is, but you know you can do that, and it's fine to check it with a sigma, whatever. Like this one, you'd have to FOIL this out, right? If we were going to do that, we're not going to spend a lot of time doing this. You're going to have a ton of these, right? But I mean, we'd FOIL that out, and then we could split it apart like we just did that. So using those summation formulas, this is what that would look like. Okay? All right. Oh, man. So that's far enough probably on the sigma. Yeah, that's far enough on the sigma. Okay. We got to know enough of it, though, to move along. All right. So I don't care about doing it. Well, what the heck? What would be the so here's just a quick short one on writing down what the formula would be. I equals 1 to how many are there here?
30.
No? I think there's 10, isn't there? Okay. And what would be the formula right here? 3i. Right? 3 times 1 is 3. 3 times what I do?
I don't know there's 10.
You're going up by 3.
Until you reach 30.
There's 10 3s and 30, I guess.
Yeah, is it 11?
Well, okay.
Well, yeah, what if it's not as easy as
Like, if
3,
you
6,
don't-
9, 12?
If you can't just tell. then
Right, okay,
three
yeah,
times.
good question. I got you. On this one, it's easy to tell.
Yeah.
But on some, it wouldn't be easy to
Yeah.
tell. Exactly. So I don't need to put the 10, right? I can put that in last. Yeah, absolutely. So and let's just say we're going to start at 1. Let's just start at 1. There's going to be a time where it'll be at our advantage not to start at 1, but you'll know when that is, and we'll get to that later. So right now, it's always to start at 1. So we're going to start at 1. So we look at this, and what I say earlier, you're repeatedly adding 3. So you're multiplying by 3. So you want to start with 3. So 3 times 1, 3 times 2, 3 times 3. I see it. So then you would just say, okay, what would the last one have to be to give us 30? 3 times 10 is what gives you the last one. So then that's how you would know. Okay? So yes, because you're going to know the last term. So once you figure out the formula, because the formula comes from the first terms. Once you got the formula, then you say, how would I get that last one? That's how you can get it. Okay? Right. Right. And you'll see, let's just do this. This would be a good one right here. Okay? Now, I'm not going to give you one even like this today. The way I'm going to give you this one is I'm going to give you this way. You see how it's much easier if we don't write them in simplified form? What would this one be? Same pattern. How would you write 4? Would it have to be 8 over 2? See how much easier it's going to be to see the pattern if you write it this way than this way? Writing them in simplified form is actually a detriment when doing sigma notation, as you're going to see. So now, give me the sigma for this one. Okay, I'm going to put a 1. How would I get a 2, a 3, a 4, a 5 on top? 1 plus I, right? 1 plus I. And what would go on the bottom? 2 never changes, right? The thing that's changing is where the I will go, right? Because the I is what's changing. It's a 1, then a 2, then a 3, then a 4. The stuff that doesn't change, like the bottom, that'll just be a 2. And now what's the last one? It's got to be 7. Now, here's one where some of you might say, would it have been smarter to just start here at 2? The top goes 2, 3, 4, 5, all the way to 8. So couldn't we went I equals 2 to 8? And then what would the top have been here? Just plain old I. But I don't care. No, this is fine. This is fine. Right? I don't care because I just said we want to start I at 1. Right? Okay? But you see how there could be an infinite number of possibilities of how you could write this? We could go from 2 to 8 and just have I on top. Okay? All right. That's right. You could go from 3 to 9 and make it minus 1. I minus 1. That's, I know. So in that way, if I give you one of these, and it seems like there's always somebody who wants to be creative and give me some bizarre one, so I can figure out if it's right. But yeah, I agree. Start it at 1. Always start it at 1 and go from there. I think that's fine. Okay? All right. Now, but I'm going to give them to you written more like this. So I want to make it as easy as possible for you to see the pattern. That's all I really care about in this, is that we just see the pattern. Okay? And if we're smart, if we go all the way back to what today's homework was, where I made you write it all out, the reason I'm making you write that all out is when you do that, it's easier to see the pattern. That's why I'm making you do that. Okay? All right. So here we go. This is the last big push, and we got to go. All right. So we're going to tie this all together now. Stuff we did yesterday, and now this notation we've learned here with sigma, we're gonna connect it all back to the integral. Okay? All right. So I've done a little bit of writing up here, and you can write that if you want. Here's our problem. So the problem is we got x squared. We're going to do the area under there from 0 to pi. Clearly not a geometric shape. This is one we could do the fundamental theorem. I've already done it up there. Right? This is one where we actually could know the exact area already, but we're going to do some approximations to it just so we can compare. Because we do know there are going to be some that don't have an antiderivative. That's what we're doing this for, learning about these approximations. But we know this one's going to be pi cubed over 3. We know it. Okay, because of the fundamental theorem. Did the antiderivative, plugged in pi, plugged in 0, that's what I get. All right. So let's write out an R4. Now, I've got my little picture over here, so I could go ahead and subdivide that, right? What would be this one right here? This is pi. So this would be pi fourths. What would this one be? Pi halves? Sure. But I'm going to write it 2 pi fourths. Remember this right here? Remember this right here? It's easier if we don't write it simplified. Okay? And then what's this one? 3 pi fourths. And actually, what's this last one? 4 pi fourths. You probably already see an I in there already. 1 pi, 2 pi, 3 pi, 4 pi. Okay, here we go. So, what is my first right? And I told you we were going to do rights. What is my first right rectangle height? How do I write it? F of pi fourths. Right? My first right edge is there because I'm doing 4 of these. My first right edge is there. I plug it into the function. That is my height. F of pi fourths times my width. What's the width? Pi fourths, because we're going pi minus 0 divided by 4 subintervals. Pi fourths is my width. Plus F of 2 2 pi fourths times pi fourths plus f of 3 pi fourths times pi fourths plus f of 4 pi fourths times pi fourths. Now, what I want to do is come up with a shortcut using sigma to write that sum. So I'm going to write my sigma. I'm going to write I equals, where do we want to start our I? At 1. I don't care. We could come up with the top number. I think you probably know what it is, but let's pretend we don't. Let's come up with our formula. Where in all of those 4 things, what is the only part of it that ever changes? The numerator and the number in front of the pi. That's where the I goes, right? Because I is going to go from a 1 to a 2 to a 3 to a 4. Most of this stuff is the same in every term, right? So what is this formula going to be here? F of I pi, that's why I picked pi in this one because I just like saying that. I pi over 4 times pi over 4, and what's the top number here? That sigma notation right there, I circled it, never look at this, circled it, you set down your pencils, you set back, we're not done, I'm sorry. But take a break, that's good. But you see that? You see by writing it out. Yes, Macy. If you start at 1, this number up here is the same as that number there, absolutely. Because this is the number, right, this is how many we're adding up. If we start at 1, this number up here is going to be the same as that. Yes, ma'am. Okay. I said earlier that there will be a time where it would be an advantage to start at 0. Right? Or something else. If we'd have done left rectangles, what would have been our first height? 0. And then 1 pi over 4, 2 pi over 4, and 3 pi over 4. Right? So in here we'd have had 0 pi over 4, 1 pi over 4, 2 pi over 4, and 3 pi over 4. So the easiest way, we'd have had all of this could have stayed the same, and we could have just went from 0 to 3. That's exactly right. Matter of fact, if you ever see in this thing we're doing with rectangles, when you see a sigma that goes from 0 to 9, that's going to be a hint. That's 10 left rectangles. 0 to 9 is 10 left rectangles. 1 to 10 is 10 right rectangles. That's exactly right. Okay, now, here's what we're going to do. What do you do if I tell you what's f of 2? Or find f of 3? What do you do? You plug it, let's say we had an equation. Yeah, if we had an equation, you would plug the 2 or the 3 into the equation. That's what we're going to do. We're going to stay in F notation all the way to here. Once we get to here, we're going to take it out of F notation by plugging into the function. So we got I pi over 4. We're going to plug that into the function, which is x squared. So this sigma, let me write it in red now. So this sigma can be rewritten as I pi over 4 squared times pi fourths. We're not going to split apart, but we're going to simplify it and pull out a constant, right? Everybody see what I did there? All I did is I took f. Okay, listen. I'll say it again. If I ask you what's f of 2, what do? You plug a 2 into the function. If I ask you what's f of I pi over 4, you plug I pi over 4 into the function. So we're going to take I pi over 4, we're going to plug it into this function. So we're just going to square I pi over 4. And then we leave and that pi fourths is still there. So I bring that along. Okay, so that's all I did. I took it out of my F notation. Now the advantage of doing F notation all the way along is it doesn't matter how complex this function is. This could be a big function with a division and a sign in it, and all of this would have been the same. we wouldn't have had to mess with all of that stuff in the function until we get to this point where we plug it in. But right now, we got that. Now let's go ahead and square that. What do you do when you square something like this? When you square a fraction, you square the top, square the bottom, right? And what do you get when you square I pi? What's I pi times I pi? I squared pi squared. That's even fun. That's even fun to say. I squared pi squared over 16, right? Times pi over 4, right? So that'd be I squared pi cubed over 64, right? Pi cubed is just a constant. 64 is just a constant, right? What did we say when we had a constant multiplied inside? Just bring it out. So this sigma, I'm going to rewrite it in black. Now I need new colors here because this doesn't get confusing. Too bad you don't have colored pencils. All right, now we got I equals 1 to 4 still. This whole thing I've just simplified to this, right? And I'm going to take the pi cubed over 64 out. And what's going to be inside? I squared. Aha. Remember I said we're putting this all together? We've got a formula for sigma I squared. What was our formula for sigma I squared? Now the pi cubed over 64 is going to stay out front. What was our formula for sigma I squared? N. So that'd be 4 times 5 over.
We're not done.
2 on top. We're not done yet on top.
Weren't we?
Which is?
Oh, yeah, you're right. I was thinking of the I.
5.
Yes, thank you. So it's 4 times 5 times 9 over 6. Okay? So that's messy. 20, 180 divided by 6, isn't that 30? Oh, that's not so bad. So 30 pi cubed over 64, which would be 15 pi cubed over 32. Now, it's easy to get lost in the weeds here of all this stuff we've done, but that is a number, and what number does that represent? The area of how many? What were they? It's the area of 4 right rectangles. Right? That's what we just found. Now, listen, I understand we could have done what we did yesterday, right, on this one. Right here, I could have taken pi fourths and plugged it in, right, and done that on my calculator. I could have taken pi halves and plugged it in. I could have taken 3 pi fourths and plugged it in, taken 4 pi fourths, plugged it in, and I could have just done that right there like you did yesterday. I didn't have to do the sigma. I didn't have to do all that, right? We could have just done like you did yesterday. So why didn't we? Why did I make you do the sigma?
It's faster.
Well, not really. I mean, that seemed to take longer. Why will some equations be harder than that? Why will some rectangles we want to do be harder than doing 4 right rectangles? Because we might want to do 100. Good, I'm glad you want to do 100, because that's what we're going to do right now. We're going to do 100. I know it's Friday. Come on, I was in Omaha. I didn't get home till like 1 in the morning, and I'm like 50 years old. That's hard for me. But I'm still excited. Okay, come on. We got all weekend to rest. Let's go. Let's do 100. No. What?
On the last slide, like, what the communication between what you wrote in red and what you wrote in black? That's what I
What I wrote in, from red to black, I just got tired of red. I thought it would all,
What did you do?
no, I thought it would all run together. Here's all we did. Once we plugged this into the function, got that. Then I did arithmetic here. I just squared this, and I I multiplied together is all I did. And then I just took that and I said, okay, now the pi cubed over 64 I can pull out. That's all I did. I was just rearranging it. That's all I was doing. Okay, now, we want to do 100. So, would yesterday's method be a good way to do 100? No, we would not want to sit here and calculate out 100 individual rectangles. But if we could turn it into this and use this formula, 100 will not take any longer than 40. Right? Because, now I'm not going to write out all 100, but what I'm going to do is start writing them. All I need to do is start writing them and then think about what the last one would be, and that's all I need to write a sigma. So here we go. Oh, whoops, I already had it. So, what is the first? Now, I might want to make myself an x-axis. Here's 0. Here's pi. What's my first subdivision? How wide are these going to be? This is still the same integral. We're still doing the same exact integral. So this will be pi 100ths. Pi minus 0 over 100. And the next one will be 2 pi 100ths. Don't you dare call that pi 50ths. Next one, 3 pi 100ths. What's the last one? 100 pi 100ths. And what's the one right before it? 99 pi 100ths. Right. So, right rectangles, my first right height is going to be f of pi 100ths times the width, pi 100ths, plus f of 2 pi 100ths. That's probably all I need to write. I think I got it. The width, pi 100ths, plus dot, dot, dot. My last one is going to be, now these are right, so what's my last right? 100 pi 100ths. Yes, we know that's pi, but it's easier if we write it this way. That would be horrible to have to plug into the x squared. It's bad enough, right? This would be, we had to plug that into the x squared and then plug that into the x squared, do all that, do 100 of them. Awful. But the sigma is just as easy as it was on the last page. I is going to go from 1 to 100. We feel pretty confident of that, but even if you don't, bring it in at the end, that's fine. This is going to be f of, the width never changes. The bottom is always 100 in here. The only thing that changes is the top. It goes 1 pi, 2 pi, 3 pi, all the way to 100 pi. That's where the I goes when you got something changing. What's the top? I pi over 100. Right? So what did we do on the next step? I'll stay consistent with my colors. We went to red. What did we do? I got tired of blue. I'm going to take I pi 100 and do what with it? Plug it into the function. So this is going to be I pi 100 squared times pi over 100. Now when I simplify that, that'll be I squared, pi squared times a pi will be pi cubed. So it'll be I squared, pi cubed. The bottom will be 100 cubed. Right? 100 squared times 100. 100 squared times 100, right? I'll just leave it 100 cubed so I don't have all the zeros. Now I can pull out the... That's when I switch to black, I think. Pi cubed over 100 cubed pulled out. Leaves me I squared. And it was from 1 to 100. Notice I left that off on some of those, which is fine. But see how this part is no more work than it was when we did 4. That's the beauty of the sigma notation. It allows us a way to write any number of these rectangles. And so finally, we got pi cubed over 100 cubed. And then what was this formula for sigma I squared? It was n times n plus 1 2n plus 1 all over 6. We'll just leave it like that for right now. Okay? And that number would be what? Area under 100 rectangles, right? Rectangles. Gosh.
That's what I said.
No. But don't write this down. We don't have time. Okay. No. All right. So we could do 1,000 rectangles, we do 10,000 rectangles, but why not, if we got a pattern, how about we just do n rectangles? Let's just do n rectangles. Now, I'm going to skip over all of this. What would be our width if we just had n rectangles? It'd be pi minus 0 over n, right? So it'd be 1 pi over n, 2 pi over n, 3 pi over n, right? All the way to n pi over n would be just pi, right? So my sigma would be f of I pi over n times pi over n, right? And when I plug that in and square it, I'd have, again, my I squared pi cubed over n cubed, right? Same thing as what we just got into doing. When I pull the pi cubed over n cubed out, I would have a sigma I squared, right? So it'd be all the same. And then this would be pi cubed over n cubed from 1 to, how many do I have? N. So now, what's our formula for sigma I squared? N times n plus 1 times 2n plus 1 over 6, which would be pi cubed n plus 1, 2n plus 1, all over 6n cubed, right? Okay, now, that would be for n rectangles. That would be the area. Question? Okay. That would be the, now think about this now. We got to go all the way back to this slide here. The exact area under the curve we know is this, right? We did it with the fundamental theorem part 2. 4 rectangles gave us this. That's not going to be exact, right? That's going to be an approximation. 100 rectangles gave us this. That's not going to equal this either, but it's going to be closer, right? 1,000 rectangles would be good. 10,000 would be good, but what would be exact? An infinite number of rectangles. So, what that means, if I would take this and think of it as a limit, as in, now wait. A limit as n goes to infinity, and we can do this, shouldn't that give me the exact area? An infinite number of rectangles should be the exact area. So let's look at this as an infinite limit problem. Well, what do? Now wait, come on. As n, yes, say it again. High powers dominate when n gets to infinity. When you FOIL this out, we don't have to, because all we care about is a high power. What's going to be the high power up here? 2n cubed. When we FOIL this, right, 2n times n, we're going to have 2n cubed. I'm so excited, I'm just shaking over here. 2n cubed, pi cubed, don't forget the pi cubed, over 6n cubed. The n cubes cancel. The 2, pi cubed over 3. Infinite number of rectangles equaled the exact area. So, here's the final result, and thank you. you. I appreciate that. Here's the final result. You don't have to write this down yet. We'll write it down on Monday. But here's what this says. What we just figured out is that if I take, this is our Riemann sum, right? This is our Riemann sum. Height times width. This is basically saying you take an infinite number of rectangle areas and add that up. That is equal to the exact area under the curve. And here's another little bonus. See how that rectangle area, height, width, see how that looks like that? People ask, where's the dx? What's the dx? I just said it's with respect to. But really, isn't that kind of height, width? Height, width. Okay? Where that comes from? Okay? This is actually the formal limit definition of an integral. It doesn't really do much for us, but it basically says the adding up an infinite number of rectangles gives you the area in the curve. Okay. Oh, man, I got this recorded. Okay, so your LH packet. Okay? In the LH packet, I'm probably gonna have to pull this up here. Just it's actually the front page of what I told you not to accidentally do. You're gonna notice it because it's got all these sigmas on it, right? So it's gonna look so you'll be like, oh yeah, okay. So on your right below what today's homework was on your assignment sheet is the problems to do on the LH packet. But I've got just a minute. I'm gonna get my money's worth today. Okay. I want to run through, the homework is very much like we just went through today. It's in that sequence, okay? So let me just quickly run through that and show you. This first one, you're just going to, they're very small numbers. You're just going to expand them out and add them up with sigmas like we started. Here you've got, look at these messy things, but you know what? They're not bad because they're written so that you can see the pattern. So you're going to write the sigma for these, okay? You can see the pattern. Okay, then look at the next group. It says use the summation formulas. So this is where we could pull out this 2, and you'd have a sigma I. Or here you could distribute this, I cubed plus I, and split it apart. Use those summation formulas. Okay? Now, the next section. Hang on here now. Focus, please. So, use those summation formulas. Then, look what this says. Find the limit as n goes to infinity. That's what we did right at the end, but they've already done all this part for you. So here you'd be like, well, high powers dominate. So the 2n cubed is the only one that matters. Put that on top of the 4, that'd be 8n cubed over 3n cubed. What's that answer? 8/3. The n cubes would cancel. You see what I mean? High powers dominate. So they're just giving you a sense of that. And then the last one, there's a couple of them here where you're going to basically do what we did on this one. You're going to go ahead and say, well, this guy could pull out the 1 over n cubed is just a constant. So I might, because n's how many rectangles, so that's a constant. So the 1 over n cubed I can pull out, I can FOIL this out, and do my summation formulas like I did on the earlier problems, and then at the end do n goes to infinity, right? It'd be just what we did at the end right here when we had, basically, you've got this sigma, which you then turn into this with your formulas, and then you do the limit as n goes to infinity. So the last couple problems are just this last bit we did here. Okay? So that's the sequencing in the homework. Okay? All right. So, well, you don't have to pay attention to me now, right? You can go watch that last 5 minutes on the video when you get home, right? You know, what did he say there at the end when I was getting ready for lunch? Okay. Or when I was already thinking about my lunch? Okay. All right. Very good. Thank you. Good job today.
I really did.
I got to do that again, third block. That's okay.
You get it?
I ate some pie. I like it.
May I take the second answer of your given?
Yes.